Hello, I'm Jeff Ward at the Connecticut Agricultural Experiment Station, and today I'm going to be talking about the return of multi-year defoliations in southern New England. So I'm going to split this talk into two separate sections. One is going to be a short, non-technical summary, which will not have very many graphs. I'll have, I think, only one or two. And then for those of you who are foresters or really want to get into the nitty-gritty details, I will have a technical discussion, which I will warn you will have quite a number of graphs. So gypsy moths were introduced to the United States back in 1868 or 1869 by a French immigrant who wanted to start a silk industry because gypsy moth cocoons can actually be made for a lower quality silk. So they were introduced right outside of Boston. Within the first year that they knew there was a problem because they were actually going across the road and causing carriages to slide. But no one did anything. By 1914, it had spread across a lot of New England. And back then is when Connecticut Experiment Station actually introduced the first spray wagon, horse-drawn. It's a pretty interesting picture from back then. And they started spraying trees as they got more sophisticated in streets. By 1934, it spread almost completely throughout all of New England. And that was during the Great Depression, and they had the CCCs. And one of the things they did, because they had so many young men and not a lot of things to do, is they'd wrap trees with burlap, come back the next day when the gypsy moths would hide under the burlap and beat the gypsy moths to death. They'd also send guys up in the trees to try and paint all the egg masses with creosote. They had some other innovative ways of trying to control gypsy moth. Here's an early version of a flamethrower that they used. And they would send guys, like I said, up in the trees, up in the topmost branches. I like all the safety equipment on there. And not just a few guys. Sometimes they would send a lot of guys way up in the trees to try to control everything. They tried controlling them out in the woods by spraying lead arsenate. And they sprayed it in the cities. And one of the great things about all these photographs is there they are spraying lead arsenate, and you can see all they're wearing are raincoats just so they didn't get soaked. Very, very different times. Well, they got more sophisticated in the 1950s and early 60s and started spraying DDT out of helicopters and airplanes to control it. But somebody by the name of Rachel Carson noticed that it's probably not a good idea to be spraying entire landscapes with insecticides, so that was stopped. So the only real control we had for gypsy moth was a virus, which once the population got high enough, would tamp down the population until it would grow up again. That wasn't until 1989 when the gypsy moth fungus was first observed and described in Connecticut. And it was actually first described by a couple of scientists at the experiment station, Dr. Ted Andriotis and Ron Weslow. And gypsy moth since then has spread throughout much of the northeastern United States, all the northeast, the mid-Atlantic, and now it's going into the Great Lakes states. So here's one of the few graphs I'm going to show you. It shows that gypsy moths were a minor problem back in the 1960s in the state. In the 1970s, we had a couple years of pretty high populations. And then the big outbreak year was back in 1981, when over 80% of the state was defoliated by gypsy moth. There were some minor outbreaks after that, and then it looked like we were building towards another big population in 1989 when they found the gypsy moth fungus, Entomophaga maimaiga. Since then, there's a one-year peak back around 2006 when we had some more gypsy moths, but there weren't any periods of multi-year defoliations until the one that started back in 2015 and lasted through 2018. So what are the effects of repeated defoliation? Well, we're pretty lucky here in Connecticut. We have the oldest long-term study in the country, if not the world. And that was actually used to study the effects of how trees were growing before gypsy moth and how they died during gypsy moth and how they responded after gypsy moth. This study was actually started back in 1926 and 1927. And one of the things that we found and others have found is gypsy moth will kill trees if they defoliate them a couple years in a row, but it also initiates a decline spiral. where those weakened trees are then attacked by honey mushrooms, also known as armillaria root rot, which can kill them. They're also attacked by two-line chestnut borer and red oak borer, and that can lead to death even a couple years after the gypsy moths have disappeared. Some of the results we found is that oaks that were growing in the shade of other trees had much, much higher mortality rates. Those oaks which are growing in full sun had enhanced mortality rates, but nowhere near as high as those oaks that were growing in the shade. Also, for those gypsy moth defoliations back in the 60s, 70s, and 80s, white oak mortality was much higher than for the red oak. So white oaks are white oak and chestnut oak. Red oaks are northern red oak, black oak, and scarlet oak primarily. We also found that for those trees that survived the gypsy moth, their growth and survival was actually higher after the gypsy moth than it was before the gypsy moth. So the bottom line on all this is that multi-year defoliations removed less vigorous trees, removed lower canopy trees, and removed white oak trees. The surviving oaks did recover and showed little long-term 30-year effects. However, what happened during that 30 years is our forest recovered with dense understories of new trees. And, probably just as importantly, the trees became 30 years older. So we went 30 years without multi-year defoliations. And if you've never been up on top of Mohawk Mountain, this is one of the great views you can see from up on top. So people, foresters and natural resource managers, homeowners, really no one worried about gypsy moths. But I tell you, there's no stopping the hungry, hungry caterpillar. It returned. And what we have been doing in the interim is Dr. Victoria Smith, the Deputy State Entomologist, and her crew have been doing aerial surveys every year looking for gypsy moth defoliation, other defoliators, other things which are affecting our forest. Pete Trencher did most of the flying until he retired doing the surveys, and that job has been largely taken over by Tia Blevins since. So here's some maps. The red dots show where there's extensive defoliation, primarily gypsy moth. And you can see we had a pretty good outbreak in 2015, but it was more localized in the lower Connecticut River region. 2016, it looked like it was going to fade away a little bit, but then it exploded again in 2017 before beginning to fade out in 2018 and almost completely fading out the last 2 years. One of the things to note on here is that there were some areas which had repeated multi-year defoliations. First time we'd seen that since the 1970s. Here's just an aerial view, and you can see all those gray trees. Those are all trees which have died from gypsy moth. And the cleared area in the center is actually an area where all the trees died, and they harvested the trees to try to get in new reforestation on Connecticut deep forestry lands. Just some ground views of the same area. The picture to the lower right, that shows during the height of defoliation in the first year in 2016. And then you can see later, you can see how many dead trees there were if you look in the picture to the left. One of the real differences, like I had mentioned earlier, is that the trees were now 30 years older, some cases 40 years since defoliation. And the trees behave very differently when they were cut down. Normally a tree falls down, some branches will crack. What happened this time when the trees fell down, they shattered. And we knew, foresters knew, and arborists knew, and homeowners knew there was something very different going on this time. So we went out and did a preliminary survey, and we worked with Connecticut DEP, Connecticut Water, Providence Water, Torrington Water, Eversource Energy, MDC. I'd like to give a big shout out to my technician, JP, and to my seasonals who also did some great work with us. So what we examined, one little bit of technical thing here, is we looked at 29 study areas for about 120 acres. We looked at 16 of these study areas had matched, managed, and unmanaged stands. That means they had a forest harvest in them. 15 of the study areas had severe defoliation, 7 had moderate, and 7 of the areas had no defoliation because we wanted to look at how the trees were going to grow. We had a drought back then, if you remember. We want to see how the trees were growing if there wasn't any defoliation. And we looked at almost 3,100 oaks. You can look at the numbers there for each one of the species. Unfortunately, we had too few chestnut oaks, only 150, so we weren't able to do a detailed analysis on them. So one of the big differences we found from before is, you may recall before, white oak mortality had been much higher than black oak mortality and the red oaks. This time around, we found out that the black oak mortality was almost identical to the white oak mortality. Other things we found, crown class, that's the amount of sun the trees are getting, was not significant. And before, trees growing in the sun had much lower mortality rates than those growing in the shades. We found that on areas that had been severely defoliated, thinning appeared to increase mortality. And this is a little geeky, but there was no link between mortality and stand oak density or basal area. So don't really know how to interpret that. So if you had a thinning, it looked like it increased mortality. But if you had a lot of trees because you didn't have any thinning, it didn't have any impact on mortality. No idea how to interpret that. So we did have trees growing back, or we anticipate trees are going to grow back like in the future. And here we have sort of a schematic of how a tree's, you can look at rings and see how a tree's growing. Well, they grow nice and steady. And then during defoliation, the rings get really tight because the trees aren't growing very fast. But after defoliation in the past, we found out that the trees started growing quite rapidly again. But the question is, that was what happened 30, 40 years ago. So what's going to happen now that the trees are older? And to be frank, we don't know, and we're just going to have to follow these trees over the year. So that is the short, non-technical discussion. If you have any questions, there's my name, phone number, and email. Phone number is 203-974-8495, and email is jeffrey.ward@ct.gov. For those of you who are interested in more technical description, hang around and we'll get into it. So this is going to be the technical discussion, and like I said, I just wanted to warn you there's going to be a lot of graphs and a fair amount of technical jargon. So what we based the original surveys on was the old series plots that were put in back in 1926 and 1927. And we've been following them every 10 years since. And we measure diameter, we measure species, or we note species, we note the crown class, and every one of these trees is actually mapped in. That's my crew from 1997. So the impact that we found, as I said before, multi-year defoliation events are important, and I'm going to show you some graphs on these. We lost most of the lower canopy oaks. We had a much higher mortality of white oaks, higher mortality of low vigor red oaks, and then we'll talk a little bit about what happened after the defoliation. So the new series plots, even though statewide there wasn't a lot of defoliation back in the 1960s, from a research standpoint, we were lucky that there was a lot of defoliation on the old series plots. There were 3 years of defoliation in the 60s, 40 to 60% defoliation. A couple years of defoliation in the 70s, over 50% defoliation. And in the 1980s, just like much of the state, we had over 80% defoliation. But we can look at 3 years defoliation, 2 years defoliation, and 1 year defoliation. So repeated defoliation, we had much higher mortality. Where we had 3 years of defoliation, you can see we had the highest mortality, the peak in mortality. 2 years defoliation, we still had increased mortality, but it wasn't as high as for 3 years. And when there's only 1 year defoliation, the mortality rates actually were the same as or lower than what the background mortality is. We had higher mortality of upper canopy oaks, whether it was during 3 years more defoliation, 2 years, or 1 year. So here's the upper canopy trees. Here's the lower canopy trees. And you can see that in every instance, lower canopy oaks died at a much higher rate than upper canopy. We also saw, especially for upper canopy trees, there's my cursor. So those are the red triangles. Mortality after the defoliation events was negligible. It was less than 1% of trees per decade died. So less than 1 out of 100 trees died every 10 years. Very, very low mortality. So those trees that survived had very low mortality. One of the things is I'd mentioned in the non-technical one is white oak mortalities. The mortality of the white oaks was much higher than for the red oaks. There's a small graph here. You can see chestnut oak had the highest mortality for both dominant and co-dominant trees. Then the white oaks, and then all the red oaks. They still had increased mortality if they were in a co-dominant position compared to a dominant, but they were much lower than they were for the white oaks. So this is a little bit of a complicated graph. So here we have diameter growth before the defoliation event. So this is diameter growth from 1937 to 1957 from trees that grew less than 1/20th of an inch to per year to those that were growing greater than 0.15 inches per year. And let's just look at the codominant, because that's the most common trees out there. And this is also survival, not mortality. So this is high survival and low survival over here on the right. So for trees which were growing very slowly, less than 1/10 of an inch per year, their survival was only about 40%, so 60% died. While the fastest growing trees, 80% of them died. So this suggests that you might want to do a thinning. What we did find, though, is if you look at the stand level, the red oak basal area, so red, the R means red oaks in the upper canopy, it actually never decreased, and it's actually been steadily increasing afterwards. Where we lost almost all of the stand basal area were in the upper canopy white oaks, so that's W's for white oak, and the lower canopy, both red and white oaks, we completely lost those. But stand basal area by 1997 had recovered to the levels that it had been in 1957. One of the other things we found is that depending upon the crown class, diameter growth actually increased after defoliation. So here's the period of defoliation when we had multiple defoliations. And after the defoliations, diameter growth rates for both dominant trees, the red triangles, and for codominant trees, the orange open triangles, dramatically increased. So the first bottom line is that multi-year defoliations removed less vigorous trees, lower canopy trees, and white oaks. However, surviving trees did recover and showed little long-term impacts. However, once again, just want to mention, we went at least 30 years without defoliation. And if you look at multi-year defoliations, we went 40 years. And then we had the outbreaks in 2015, 2016, 2017, and 2018. Again, just another view of patch hog, just reminding us all, we had these large areas of mortality. You can see here where they had some harvest. See some in the background. I don't know how well you can see it, but if you look in the upper right hand, you can see how entire hillsides are just completely gray with dead trees. So the question for foresters and natural resource owners, managers is to cut or not to cut, and what to cut. Do you take out vigorous trees, red or white oaks? How many years has it been defoliated? What are the market conditions? And one thing to remember is that dead trees don't resprout. If you cut down a tree before the defoliation and you have sprouts, well then you might be able to have some new oaks in the next forest stand. So we went out there, like I said, we did a preliminary survey and the first year, and we were really surprised. We found that, whoops, let me go backwards. Don't know how to go backwards, but anyways, as the earlier surveys, white oaks had much higher than red oaks, but now red oaks had much higher, had about the same mortality as red oaks. Again, just a quick summary of what we looked at, a lot of study areas. We spent a lot of time out there, and over 3,000 oaks were examined. If there's a couple geeks out there, we did arc sign transformation mortality rates to normalize, to increase normality of the mortality. We also, the models we selected had the lowest AICs with significant factors. At the stand level, we looked at linear mixed model analysis with study areas as a random. And at the tree level, we used binary logistic regression to try to see which individual tree factors were most important. With all that said, And this graph is a little mislabeled where it says year. It should actually be the Palmer Drought Severity Index during growing season. It was surprising, we had this big outbreak recently, from 2015 through 2018 during a period of drought. But if you look at the other outbreaks, they aren't really correlated with periods when we had severe drought. So drought isn't really an initiator of the defoliation. We also found that pre-defoliation stand level mortality. So what were the mortality rates before the defoliation? They didn't differ between managed and unmanaged stands. Mortality rates were the same if you managed or didn't. It didn't differ by the amount of oak that was measured by basal area or by density. I will say we didn't examine soils, but we did see when we looked at post-mortality, we saw high mortality on some some stands that had moist soils. One of the other important things we were kind of curious about is, okay, so were these stands where the trees were already had high mortality before the gypsy moths came in, and that's why they had high mortality afterwards? And actually, there was no correlation. That was a bit of a surprise. Stands which had some stands with low mortality before the gypsy moth had high mortality during the gypsy moths. Some stands with high mortality before the gypsy moths had low mortality. It was all over the place. Just a view, this is over on Eversource property. It's over on Maromas by the Connecticut River, showing the defoliation back in 2016. So let's talk about individual tree mortality rates and not stand mortality. So here's our sample size for areas that were severely defoliated, had moderate defoliation, and had no defoliation. Especially for red oak, we had large sample sizes in all of those. So what about the drought effect? I said, we didn't see that at the stand level. Well, here's what I want you to notice that. If you look at, for each one of these three species, for red oak, black oak, and white oak, and here we have 3-year mortality rates. We put everything at 3 years so we could compare them. So the yellow bars, the leftmost bars, are what the mortality rates were before defoliation. And you notice that in areas which had no defoliation, those are the second to the left, the green squares, mortality was actually lower during that period on stands that had no defoliation. So drought was not causing increased mortality. But if we look at the amount of defoliation, if they had moderate defoliation or severe defoliation, for every species, for red oak, it went up from, less than 5% to almost 30%. For black oak, around 5%, up over 40%. And for white oaks overall, it went from about 6 or 7% up to over 45% mortality. So the more defoliation you had, the more years of repeated defoliation, the higher the mortality rates. So this is really geeky. So let's look at areas which had moderate defoliation. And what we did, like I said, is we used logistic regression here. The open circles, or the open symbols that aren't filled, were non-significant models. The ones which have closed figures are significant models. And you can see that in general, with increasing tree diameter, we had lower mortality rates on those areas which had moderate defoliation. And if we look at 10-year diameter growth rates, you can see that for all three species, if trees were going over 1 inch for red and white oak, there's almost no mortality. For black oaks, it also steadily decreased as diameter growth rates were growing. What's interesting is that black oaks for a given size and for a given growth rate had higher mortality than for red or white oaks. Here's the depressing thing. In areas which had severe defoliation, and severe defoliation is where they had at least 2 years of over 50% defoliation. If we look at initial tree diameter going from 0 up to 20 inches, there was either no significant relationship or an increase in mortality for white oaks as the trees got larger and larger. Very depressing. If we look at diameter growth, there was, again, for northern red and white oak, there was no significant models. There was a a trend, if you want to say, for white oaks that it tended to increase with increasing diameter, mortality increase. For black oak, though, mortality rates actually decrease as the trees were growing faster. So at least for black oaks, there's some evidence that if we did some thinning, it would decrease mortality. But again, crown class was not significant, and that's mostly because we had very few lower canopy oaks. Almost all the lower canopy oaks by this stage in stand development and after previous gypsy moth defoliations were gone. Thinning increased mortality of red and white oaks on severely defoliated plots. Boy, that makes you wonder, especially when we don't know that, or we couldn't find a link between mortality and stand oak density or basal area. I really don't know what to tell you on that. I wish I did. So in summary, we didn't find any effect of drought. We think you can reduce stand and tree mortality by removing black and white oaks. The thinning effects are uncertain. And if you anticipate severe, heavy multi-year defoliation, so you've had 1 year defoliation and you see there's a lot of egg masses out there again, you can expect high mortality, and you know what? We cannot predict which trees are going to die, which is too bad. So what's going to happen in the future? Line spiral. So we get the forests that are, think of, a lot of us saw back in the 80s and the 90s. We expect those surviving trees to have recovered diameter growth. But the thing is, now these trees are much older, so we don't know if they're going to recover. That's what we're going to have to find out over the next 20 years. We just don't know. And how are the stands going to recover? Well, one thing we do know is that if you cut an oak, the older trees don't sprout as much. And if they're protected from deer browse, and this is a stump that we actually put a cage around, this is what it looked like 4 years later. Outstanding growth. But we have a problem with deer in a lot of Connecticut, and there wasn't a big deer problem back in the 60s and 70s. The deer population has exploded since then. So in areas where you've got a deer problem, here's another one. Here's 1 year where we put a cage around an oak, and you can see it's already up 6 feet high. Here's an oak right next to it, which wasn't protected from deer browse. That oak is not going to have a chance. It's just going to be repeatedly browsed. We also have a problem we didn't have back in the 60s and 70s. We have all this interference from non-native invasives. How is that going to affect our regeneration? Maybe the forest that we're going to have in the future is going to be beech and birch. And if you actually look underneath here, you can see some barberry. Not a happy sight. So if you have any more questions, please go ahead and give me a call or email, and be more than happy to talk with you. Have a great day.